All right, so let's get started today. We're going to do iterators in Python. So the objective today is to understand how iterators and for loops work under the hood. So for loops are pretty important in a language like Python. You see them everywhere, and we haven't. If you notice, all the code we've written or looked at so far hasn't had any loops in it. They've just been straight line code, if statements, maybe function calls. We haven't had any loops. And the for loop in Python is sort of different than a for loop you would expect in a language like C, which is really just counts up stuff. So last time we covered functions as PyObjects, so we're actually going to really take a change this time. It's going to be a completely different topic. And today, no to-do. So today we're going to do, we're going to go over a Python for loop, going over a list, and then we're going to look at these three files, and then we're going to show you how to define a class with a custom iterator. So a list is a built-in data structure in Python with its own iterator. So a lot of Python built-in data structures have iterators already, but you can also define a class with your own iterator. So has anyone heard of a concept of iterator before, and you kind of want to summarize it very kind of abstractly? It's kind of hard to come up with a idea.
I mean, it's a collection, and you could repeatedly call, and I'm thinking of Java iterators, where you repeatedly call next to get the next item, and you could just, a lot of times they have a while has next. Right,
there's a has next.
That you can check as a condition.
Yeah, so, basically you're pretty much right that the iterator itself is not the collection. Every collection has an iterator thing. So the iterator is just some abstraction for iterating, because it's a pretty bad circular reference. But yeah, so iterating is sort of the act of doing something again and again, like in a loop or in a sequence. So to iterate over a sequence or to iterate over something. And an iterator is a object that encapsulates this act of iterating, I guess. And the iterator object has really just one method called next, which is just give me the next thing in my iteration. And then there's also sometimes, in Java, there's a has next. Python doesn't have this, but there's a has next in Java that checks, do you have another thing still? So in Python, it actually just uses an exception handling to catch up. It's the same idea, that you basically, the only thing you can do with the iterators is to call next on it. And so conceptually what happens is, imagine you have a list. You have a list of stuff. You have a list of elements in whatever language. Here's a list of letters. It's H, E, L, L, O, 1, 2, or whatever. I didn't put the quotes in. So the list object, this thing is a list, right? So LST is a list object in Python, whatever language. So one thing you can do is you can create an iterator on the list that you can actually, in Python, what you do is you either call iter, the iter function on list, or list has a dot underscore underscore iter method. It's the same thing. And basically by doing that, let's say you have I equals this. We'll show this in the code. When you actually do this, I is actually now I refers to some iterator object. And what the iterator object does is it's not the list, but it actually has a pointer to say the first element of the list. And then when you call dot next, when you say I dot next, every time you call I dot next, it will give you the element. So the first time you call I dot next, it will give you H, it will return H, and then it will advance this pointer to the next thing. And then when you call I dot next again, it will give you E, and then it'll advance the pointer to the next thing, and so on. So, and in Python, what happens is if you keep on calling next, this pointer keeps on moving, it keeps on returning the next thing, and then at the very end, when there's nothing more, it throws an exception. So it says, oh, I'm done, and it raises, I think it's called the stop iteration exception. So it raises an exception at the very end after it's done. So your code for using iterator would catch this exception and say, okay, we're done. So the important thing about iterators is that every iterator object has a pointer to its current element, and it can only advance forward. It can't go backwards. I think Java has these bidirectional iterators, but the simplest form iterator just goes forward. So if you want to create another iterator, you just create another one. You say j equals iter list or whatever. And now j is a, this thing's getting messy. So j is an iterator object, and now j points to the front. So a list is just a single list, but you can have a bunch of iterators to it in terms of different places. So one way this could be useful is you could, one way this could presumably be useful is you could actually have two iterators. I'm just going to use a shorthand here. I'm just going to use an arrow to mean the iterator. Even though, you know, an iterator thing is an actual object, and inside there's a field pointing to some, say, some element in the list. So you can imagine iterating over two things like that in lockstep, right? So you have a, you know, a prev and a cur, and then, you know, you do something with these two elements, and then you advance the cur up to this one, and then you advance the prev up to this one, and then you keep walking up the two of them together. So you can actually have two iterators over the same list, and it doesn't modify the list at all. And usually the iterators don't support modification. I think the Python ones don't. Remember how we try to iterate over the dictionary, and then we try to delete something, and I said, oh, you're not allowed to. Some, I think Java iterators, some allow you to have mutations. Is that right?
I've never done
Yeah,
that.
it's not a good idea. I mean, if you can imagine, because when you're walking over a list, if you kill this thing, you know, and you jump over it, and it's weird. So I guess the question I have for all you is, why do we even need an iterator? I mean, why don't we just say list 0, list 1, list 2? I mean, the list is it's directly indexable. So why do we need this concept of an iterator at all? Ideas there?
Make the code more short and sweet.
Yeah, so one, you can make your code shorter, that you don't have to keep writing a number every time. Otherwise, if you don't have an iterator, you have to, you know, basically do like a C-style for loop where you have a number, you know, I equals 0, and then I plus equals 1, and whatever. So that's really good. That keeps the code shorter. And I think on a related point to that, are there other ideas for that?
It keeps you from going out of bounds. You don't need to know how long
That's
the
true.
list is.
That's true. That's a good point also. So you know, you don't need to you don't have to worry about going out of bounds because it bounds you. And I think these 2 points are actually getting at a similar point, which is this abstraction of iterators helps ease your code, right? You don't worry about the indexing. You don't worry about going out of bounds. And the nice thing about the iterator is that it makes it so that you can iterate over arbitrary objects, right? So imagine if I had, the list one is pretty simple, but imagine if you had a, wow, how do I actually, can I just select this whole thing to delete? How do I do it? I go like this? Yeah, I can do that. Oop, there you go. So imagine if you had like a weird tree structure that you define, right? Like not even a binary tree, like some like arbitrary, you know, tree for some data structure for your system's thing. I don't know, like it's some tree and this has children and this has like 5 children or whatever. You know, you might want to return all the elements in this tree, right? You might want to define a function that returns everything or walks over every element and does something, right? Like you want to walk over every element, and maybe these are numbers and you want to increment them by something, right? So imagine an algorithm going at trees. If, you know, trees aren't super easy to index, right? You can imagine, you know, if the root is R here, you can say like R0 and 1 and 2 and whatever, right? And then that goes to 0 thing and the 1 thing, and then, well, there's no 2, you know, 2. So I'm just imagining if we could index the children in the tree, you know, R0 is the first child, and then this 1 is the second child, and this 2 is the third child. We get that one. And then you can imagine manually updating all this yourself in your tree structure, or manually going over and getting all the values. That's just really annoying. You have all these indexes, or maybe you have to say like r.left child, you know, r.child, you know, 2, or I'm just making these things up, but like you have to get at it different ways, right? Like you need some way to get to it. But really what we want is, maybe we just want an iterator that just gives me every element of the tree in some order. So maybe one order is a pre-order traversal where we give you this one first, and then this one, and then this one, and then this one, and this one, and whatever. Maybe it's an in-order traversal where you go, I don't remember all the orders, but you can imagine how you can give the elements, or maybe you don't even care about order you get them in. I just want all the elements so I can mutate each one or add each one to a collection. So then what you can do is you can actually, in your tree class, this we talked about in the second half, is we can actually create an iterator for our tree class. And conceptually what happens is all of them we have to do is we just have to say, what is this, R? R is our root of the tree. We just have to say R or iter R, I equals iter R, and that will give me an iterator object. It's some iterator object. And then this will start pointing to whatever the first element is. I don't know. It depends on how you define it. Maybe it starts pointing to this one, because the iterator object will keep track that it's pointing to this one. And then when you just call i.next, it just gives you this element, and then it just moves the pointer to the next thing, and then i.next again gives you this element, moves the pointer to say this thing. I don't know the order because I don't know what your iterator is, but the idea is that it's a very elegant interface because all you do is create an iterator and just keep calling next, and it'll just give you the elements in whatever order the iterator defines. And again, you don't have to worry about out of bounds. You don't have to worry about indexing. When it's done going through the whole tree, it will just say we threw an exception and we're done. So it's this one very kind of elegant interface for iteration. So the kind of long-winded way to say this is iterators are a abstraction for iterating over anything. Yeah.
When you're iterating over a list, can you kind of have one object for int and then the other object for a tree, and then is that also a part of the arbiter?
Oh, sorry. So you're saying do you want to?
Can you do like with different types of have it
Yeah.
iterated with different types?
Yeah, that would be cool. So imagine if you had. That's pretty cool. So the question was, can you imagine an iterator that goes over different types simultaneously? Yeah. So imagine if if you're making a custom data structure, you probably have different types, or you might actually have a. This might be a tree, but each node might actually be a list of things, right? This node might be a list, this one, and then you just have to. I mean, it's all up to how you define your iterator. So if you define your iterator when you're at this tree node, when you hit next, you better go in the list, and then go in the list, and go in the list, and go in the list. And when you're out of the list, you better remember to go back to this tree node. So it's all in how you code your iterator, but it can basically do anything. Cool. Okay, so now we're just going to go over. For the first part of the class, we're going to go over just iterating over a standard list. So I'm going to go to our, we're just going to go to Python prompt, so no interpreter yet. We'll have you do some of the more interpreter stuff in the exercises. But okay, so we'll just say, hold on, let me see, A, B, C. Okay, so we're just going to open Python. We'll just say x equals a list A, B, C, just 3 strings. You can all follow along here. So it's just a standard list, 3 elements. We press enter. X is a list. Okay, so not super exciting. You can directly index the list. I said earlier, x0 is A, x1 is B, x2 is C. You got nothing new at this point. And then what happens if I do x like 3? It'll just be an error or some error. It's out of range. Just index it. Just throw some exceptions. So if I say x equals 300 or whatever, just out of range. So we'll call again, I just use Control L to clear the screen. So x is a list. So we can get an iterator out of this list, or an iterator that points to the list by calling, we'll say I equals, we'll call it, we'll use the underscore iter. It's the same thing, both. So every list has a special method inside called underscore iter. And when I actually do it, so now what I is actually a, it's a special object called a list iterator. It's a list iterator object. Right, it says right here. So when I print out I, it's a list iterator object. And this list iterator object has some kind of reference to the first thing in this list because we haven't started yet. So when I actually recall the only thing I can do with I is call not next on it, pretty much. So when I call next as a method, I'm going to press enter, and what should it return for us? A. Good. So it returns A. And now what happens is that inside there's some reference that there's some reference that will update. So this will somehow update to point to the B, and then not surprisingly, when we hit next again, goes B, and then this will move on to C, and then hit next again, goes on to C, And then now there's probably some state inside that says like, that says like we're done or something, like, we're done. This iterator is exhausted. It's done. There's no more. And so when you actually try to call next again, it'll raise an exception. And the exception that it raises is called a stop iteration exception. So you can imagine writing a loop like this now. Now actually let's just create a new one, because now if I call I.next, I'm done, right? I can't do any more. It's already dead. So we could make another iter call, where is it? X is our list. Remember, X is still there, right? Nothing changed with X. So we can say J equals X dot underscore iter. So J is an iterator. So we can imagine something like while true, colon, and indent, print J dot next. All right, so we're just gonna keep on doing J dot next forever, and then and print it. So what should this print out? Okay, ABC. And then what happens after you print ABC? There'd be an error, right? So it actually doesn't look super nice, but yep. So it does what you want, but then it throws an error. So how would we prevent that from happening? So let's try again. So we need to somehow catch the error, right? So we haven't talked about exceptions in this class, but it's basically a try except block in Python. So except stop iteration. Oops, stop iteration. And then pass. Pass just means in Python, don't do anything. Because in Python, everything has to be indented. So if you don't put a pass here, it will give you an error because you have a colon. So you need pass just means no up, like don't do anything. But because Python, we need to indent everything. Basically a block with no lines in it, you need to say pass. Because otherwise, if you try to write the next line here, it will give you an error because your colon expected you to indent your code. It's just a Python quirk. It's just because it doesn't have braces, right? If Python had braces, you can do that. So what this code says is while true, run forever. We're gonna get .next and print it. But if there's an exception, that's the stop iteration exception, just don't worry about it and let it go. Actually, this is bad because this will keep on going. All right, I should do that. Yeah. So what should we do instead of pass? Yeah, break. Yeah, good catch. Right. So when you hit that, we just actually get out of the loop because pass means we keep on going back. Good. So if we do that. Oh, J. So what happened here?
G has already expired.
All right, good. All right, I didn't plan this on purpose, but that's right. So we'll use the other form, iterx. It's the same thing. Iterx and x dot underscore underscore. Iter is just a built-in method that grabs the underscore iter. It's just a convention. So now let's try the code again. While true. Okay, so, and if you're typing in the prompt, you need to type enter twice because it thinks you're still entering new code. And lo and behold, we got what we want. Good. So what do? We basically have a loop that always runs, finds j.next, does something with it. Here we just print it, and if we ever hit the stop iteration exception, we just break right out of the loop, and effectively prints out every element in the list and cleanly exits. So this is good. This is exactly what we wanted to use iterators for. So you can imagine you do this for every other data structure. So it turns out Python actually has a shorthand that allows you to do this much more compactly, and it's just called a for loop. So if you actually just say for, say, element ELT and X colon print ELT, if you do that, that implicitly turns into something like this, more or less. It basically, well, instead of print, it'll actually just assign it'll assign element to this next, and you do something with the element. So the nice thing here about the for is that you don't actually have to define an iterator object. So when we run this, it does what we think we expect. So the for loop inside is actually making an iterator object and assigning each thing the iterator returns to ELT, so you can do stuff with ELT inside the loop. Does that make sense? So it's all behind the scenes. It's all hidden from you, but we'll actually dive in this class. And this is nice because this prevents you from having to explicitly do the while loop and create the iterator stuff. But if you want to have more fine-grained control, you can create the iterators yourself. So for these built-in data structures in Python, usually people don't explicitly call the iterator. I just did this just to illustrate the point. Usually just write for loops. So imagine now you kind of are starting to see how for loops work under the hood. So let's say X is a dictionary, which is a key value mapping. So it's a mapping of people to their ages. So let's say John is 50 and Jane is 49 and Joe is 12 or something. So X is a dictionary. So when I say for elt and X, print elt, what do you think this should print out?
Key value pairs.
Okay. So people tried this in Python. So this actually just prints out the keys. So the iterator for a dictionary, again, it's just how they define it. You could define it as key value pairs if you wanted to. The iterator for a dictionary in Python, the built-in iterator just does the keys. And notice how there's no order either, even though that's notification thing is really annoying on the. There's no order, even though these are kind of ordered. But the dictionary iterator isn't guaranteed to have an order, because a dictionary, these three elements are just like key value mappings. Like they're not guaranteed to be any order. So when you iterate over it, you could have gotten John, Joe, Jane, or Jane, Joe, John. You can't really guarantee an order. It happens that it's in order here, but it's just a coincidence. So in this way, it's actually creating an iterator over the dictionary object and going through it and doing its thing. So you can imagine iterators over all sorts of other objects. So what happens if I have a string, hello world? If I have what does the iterator over a string iterate over? For elt and s, print elt. What do you think this will do?
Letter by letter.
Yeah, so it's one character at a time, one letter at a time. So the strings iterator, so let's try it. So I equals iter s. I is an iterator over a string, so I.next. So what should this print out? So remember, s is hello world. What should the first call print out? Yep, h, and then the next call, and it just keeps on going until it dies. Well, okay, so I think we have a pretty good idea of the basic thing behind iterators. So now we're going to go into the interpreter itself. So we kind of did the overview in Python. Now we're actually going to the interpreter. So the code we're actually going to be interpreting is this iterators.py. It's basically what I just wrote. And notice how this actually it doesn't create an iterator explicitly. It just does the for loop. So the for loop has to create the iterator for us. So for next print e. So you can follow along if you want, or you can just look on here. So x is just a list of 3 strings, and we're doing a for loop and printing. So if we run this, not too surprising what happens, and we're going to disassemble it. So we're going to do Python this. So let's see if it all fits. Make the font a little smaller. Let's try it again. Small font. Okay. The first line is not super interesting. This is just creates the list. So this is not super interesting. So this, you've seen this in the load tuple example from last week's homework. Just load 3 constants. Build list is what you can imagine. It pops all 3 off the stack, makes a list, and then stores it in X. Not too surprising. And then the interesting part here that we'll kind of study is this. This is basically the for loop. So there's a setup loop bytecode, and then there's a pop block bytecode. This is not super interesting. So some of you might have seen there's a block stack in Python that represents kind of blocks of execution, like you have a loop, you have another loop inside and stuff. It's just as bookkeeping so that it can keep track of loops and exceptions and stuff. So basically what this says is setup loop 19 to 37. It means setup loop, and this loop goes down until line or instruction 37. So that means that every piece of code inside of here, from there to 37, is in the loop, and inside is code for the loop, which is kind of indented, right? It's been indented inward. So if you can imagine, try to look at the code in another terminal. Whoa. Remember, all this code here is, line 2 sets of the loop, and all this print E stuff. All this stuff is inside a block. A block in Python is an indented thing. So let's go back to here. So set up loop and pop block. So that kind of delineates what the loop is. So what is the loop? The loop is we first load the name. So I have to remember the code. The code is what? For E in X colon indent print E. That was the code, right? Okay. So this for E. So this load name loads X. Loads the value of X. Get iter. We're going to study this in the interpreter. This gets an iterator from X. So conceptually what this does is it expands this into, after this, it grabs whatever is on top of the stack, which is X, and then it gives us an iterator. So it basically just says, the thing on top of the stack now is actually iter of X, whatever we call iter on X. Or, it's either iter or of X, or alternatively X dot underscore X dot underscore iter underscore call. So recall that this is, when I say I equals that, this is actually an iterator object now. We'll go in the interpreter to see this. So now we took X, whatever this was. Remember, if you actually just look at this code, you don't know what this is. You don't know that X is a list. X just happens to be a list. But this for E and X could work because iterators are so generic. It could work for anything. It could work for a set. Your weird tree list combo hybrid thing. It could work. You just do a for loop over it. It just it just gets the default iterator over it. And now for iter is some kind of command, bytecode, that goes to 36. So this means that when you're done, we're going to go to 36. And this sort of is defining the for loop. And inside the for loop, every time you do something, we're going to store the thing you're iterating over into E, because E is the variable name. So for E and X means we're going to keep going over X and store everything in E every time in the loop. So conceptually, I'll just say iter X. It's the same thing as the other one. Conceptually, what these few lines do is it sets up an iterator I equals iter X, and then it says, E equals I dot next. And E is used here because E is here. So we made this another letter, it'll be another letter. And basically, every time you go through the loop, we're going to assign E to I dot next. And we're going to keep on doing that. We're going to keep on doing that until we stop. So now inside the loop here, everywhere inside this loop, we actually have access to E now. So what do we do with E? All we do is just print it. It's just a simple print. So it loads E, prints it, and then prints new line. So print item just prints whatever E is, which calls some print method on it, and then print new line just prints a new line. And what does this jump absolute do? Go back to where?
Starting.
Yeah, to 22. Yep. So this is just a loop. So that's where the loop is. So it basically, the execution goes down, and then it goes down, and then it goes back up and down and back up, and it loops until what happens?
The end of the iterator.
Yeah, until the end of the iterator. And that's probably for iter here, right? This instruction, because this says go to 36 when we're done. So at the top, this for iter checks, and if it were done, we would go down to 36, which is down here, and then we exit our function. Make sense? So we, let me clear everything. So basically the execution goes straight down, and then the for iter sets up here, and then jump absolute jumps back up to here. Then we're going to keep going down and jump back up. And then for some time in the future when we're done, it says we're going to jump down to 36 when we're done, and then we keep on executing and we get out of the function. Okay, so we're going to focus on, when we look in the interpreter, we're going to focus on mainly on for iter. I mean, we do get iter also, because we need that as a prerequisite. So remember, get iter and for iter, they follow each other. Okay, so let's start diving into the code. We're going to open CEval again, so Python, capital Python, and then ceval.c. And just look up get underscore iter. It's in 2493 if you have a fresh copy of the code. And this takes the top of the stack and calls PyObject on it, which it gets the iterator, which is not super surprising. And then it decrements the reference to the original object because we want to get it off the stack. And it sets the top thing to be the iter. And it does this prediction thing because it get iter oftentimes is followed by a for iter, so it does this direct prediction like we did for assignment 1, right? The prediction means if we actually succeeded, we're just going to jump straight to predictor with our to here. We don't have to go back. We don't have to go back up to the main loop again. So the nice thing about this is get iter and for iter usually just run as one continuous sequence without going back up the interpreter loop. If because they follow each other. So it's just a nice optimization. So let's dive into what get iter is. So we're going to assume we have a list. So in something like assignment 1, it's enough to just say, oh, we just call PyObject iterator, we just get an iterator. That's enough of a comment. But since we're getting more advanced here, we need to dive in and see what this stuff actually is. So PyObject get iter is in abstract.c. So if we actually go up one directory, objects, abstract.c. Remember, this is the generic, abstract.c is the generic object interface. And we do the generic interface, we don't know whether it's a list, right? We happen to know that it's a list, but this opcode needs to be run on any piece of data. So let's find it right here, 3067. So let's see what this code is. It's not too big. So you can kind of read it off at this point. Remember, everything has a type. Every object has a type. If this type has a feature, TP flags have iter. So some types just happen to have some iterator type. Then we actually grab the TP iter method on the type of the object. So we actually grab the object, we grab the type, and we grab this TP iter. If there's no TP iter method, then we actually see if it's a sequence. If it's a sequence, we actually create a sequence iter, a seq iter object, which is a sequence iterator. So there's actually two kinds of, because again, there's an optimization, there's two kinds of iterators in Python. There's a sequence iterator, which goes over a list or a string or whatever. And then there's a generic iterator type, which relies on calling functions. So for now, let's just go to the sequence iterator. We'll actually have you do the other type as an exercise. Actually, that's a good idea. We'll actually have you discover what the other type is during your exercise. So let me. So we have a list. So the reason why we have a list is that this have iter will be false. So we're gonna look in the list object. So you have to follow on, but I'll go to list object. This is TP iter. List iter. Right, so the list type, so this is a list type. Remember how every type has some big heading? This doesn't have the has iter on. These are the flags. They don't have it has iter. So it's weird because you're like, wait, lists have iterators. But yeah, it's a special kind of iterator that's just for sequences. So this will return actually false for a list because it doesn't have a special iterator method. So if you actually look at TP iter, well, actually, it does have a list iter. Actually, yeah, but I don't think it uses it because this flag is not on. Yep, so the flag I'm trying to search for it is not found. It's not in the list. So if that happens, then we're going to go into, if it's a sequence check, a list is a sequence. So you can just assume this checks out. We're going to create a PySeq iterator new. So where was the context? The context was, you need to remember where we were. We were in for e in x colon print e. X equals A, B, C. So we're trying to do a get iter on X right now. We're trying to get the iterator out of that so we can actually use it. And the process of getting iterator out, we're going here because we need to create a new sequence iterator, the special sequence iterator type. Okay, so what does that do? So this is in iterator.c. So again, objects. So now we're going to dive into iter object. Sorry, did I say iterator.c or iter object.c? I think I said iter. Oh, whoops, that's weird. It's actually iter object.c. I think I wrote it wrong in the. Let me double check the syllabus. I'm going to write myself a note to create the right thing on the syllabus as well. Iter object.c.
Why is the flagging set? The 3071 flag.
Sorry?
I think the flag is set, right? TP flag have iter
Yeah.
in the object.h.
In object.h it's set?
Yeah, 586.
In list object.h?
Object.h. Line
This one.
586.
Oh, this is just a this just defines what the flag is.
Oh.
So flag is whatever, one shifted down seven. So flags are basically here. I'll talk to you about flags. 1 second. Let me write down the iterator notes. Iterator. I can't spell iter object.c, not iterator.c. I made a typo in my notes. Also. Okay, so a brief note on flags is this is not super essential to this class, but since you brought it up, what are all these flags? So for those of you familiar with C, what is 1L7 whatever? What does that mean for those familiar with C?
I think it's one shift that 7 bit.
Right. So the number will be like
0,
0,
0,
0, 1. I don't have 1, 2. Is that right? Yeah, something like that. And these are all bits, right? 1, 2, 3, 4, 5, 6, 7, 8. So this number is actually that, right? And then 1 shift 6 is there. 1, 2. No, I think I'm missing one, right? I think it's that, right? Because 1, 2, 3, 4, 5, 6, 7, and 6. Is that right? So 6 is this, and 5 is, you can imagine that. So all a flag is in this definition is just a number. And the reason why these numbers are set this way is that you can actually do an OR. I just missed it. You can do an OR of them, right? So if you say TP flags have iter or TP flags have weak refs, by ORing them together, you actually get a flag called I don't know. Your flag is. Oh, just imagine this is the case. So if every flag just has 1 bit and you do an OR of them together, you actually get like the combination of the flags, and they don't overlap. So it's just a very compact way of just giving a bunch of booleans, right? So when you're, that's why in your list object, so all these flags are a bunch of ORs, if you see that, right? So this is an OR operator in C. So what this says is that this is just one number. I don't know, it's like a 1 byte or however many big number. This number happens to be like 1, 0, 1, 1, 0, 1, 0, 1. Then every bit in that number represents a flag that's on. And it's very convenient because it's very compact, and you can test which bits are on by just doing an AND with the complement. Well, you basically do a mask. I guess you do an AND with right. So you actually do an AND to test whether it's on. So let's say I want to test whether this flag is on. Then we do an AND of this, and these are all zeros except for that, and then we check if that's 0 or not. And if it's not 0, that means that flag is on. So you can use a bit mask to test the thing. So that's all that thing means. As far as you're concerned, it's just the flags are just a way to check for whether a property exists. It's just 1 byte, 1 bit, and it's compact because it's just 1 bit. Okay, so we were at PySeq iter. So we're at objects iter object.c. So that the context was okay. So remember the context. We were in get iter. We call PyObject get iter. Then in abstract.c PyObject get iter, we don't have the special iterator flag. We are a sequence, so we're going to create a new sequence iterator over our sequence. So now we're here. We take a sequence in. The code is not super interesting. It just creates a new sequence iterator object, whatever that is, and and then it sets the index to 0, sets the sequence to the sequence it's tracking, and then it just returns it. So it's like, what does this mean? So the two essential lines here are that it index is 0, and the sequence is the sequence you passed in. So a sequence iterator object, a sequence iterator has two things in it. It has an it index equals, say, 0, and it seek, which points to the original, say, list, right? The list of A, B, C. So it actually keeps a numerical index. It doesn't actually keep a pointer to the thing, which is interesting, but it's fine for lists or strings and stuff. So you can imagine when we call next on this, it will actually just index the list at 0 and then make this 1, index the list at 1, make this 2, and so on. So a seq iterator is just a sequence iterator actually just keeps a numerical index, just how it's implemented. And okay, so it creates an iterator. All right, so now after all this work, we have an iterator on the stack now, and then we get out. So recall the context behind all of this complication was that we wanted to do the get iter, right? So we loaded x. Now whatever's on the top of the stack is not x anymore. So x was this list, or is this list of A, B, and C. Now what's on the top of the stack is some invisible I, which we can't see, and this is a sequence iterator that happens to point to, the x object, and also has a it index of 0. So we have an iterator. Now we can actually start using it. So the for iter is where the kind of the main content of this whole thing is. So let's go to for iter, which is right down here. Okay, so what does do? Okay, so it goes here. Wow, this looks like a big jump. So what does this line do? Could I interpret this line? There's a lot of stuff in there. We're just conceptually just kind of speaking it out.
It just calls the next method.
Yeah, it just calls the next method. On what?
On V, there is the double step, the next, like the iterator, I think.
Right. It calls the next method on the iterator object itself, not on the actual x object.
Yeah.
Right. So right now, this iterator, right. So it looks up V. V is the iterator object. It looks up its type, and then it looks up TP iter next, which is hopefully some function. It grabs the function. This is a function pointer. It dereferences it. It grabs it, and then it calls it as a function call on itself, on the V itself. So that basically is saying calling v.next. Because really we need to find the next method of v and then call on itself. So in an object-oriented syntax, it's basically v.next. Because when you actually are running code in an object, self is the v that you're passing in. So this does v.next, and then this will say x equals v.next. And then what do we do with x? We if it's not null, we push it to the stack, and then we predict store fast and unpack sequence, because this is what next is going to happen. Right? We actually want to store this into a variable. So where does this correspond to in our code? It corresponds to this, right? We do a for iter, and then when we actually grab the thing, we actually store name into E. So that's why it predicts store name, right? Because the for iter, it knows that after it tries to call next, it should store it into a variable right away, called something. So when we say for e in x, each time the iterator goes and calls next, it stores in a thing called e. If we actually name this something different, it'll be called something different, right? If we say, I'm just going to modify the code just to make it really clear. For element in x. Oops, now let's give it an error. Does the same thing. I mean, essentially does the same thing. And if we disassemble it, it just stores an element, right? This variable is just called element now. Okay, so now we actually stored it and do it, and then we can just keep going and do whatever we want with it. So, but the other case we need to handle is if we're done, right? If we're done, we need to get out. So let's look at the other case. So let's go back here. So this is the correct case where everything works. If there's an error, then we do some exception thingy. Jump by op arg. So this is what happens when the iterator is done. So notice how in the correct case, it actually does a continue. So when we go into for, well, actually let's go up to get iter first. So this mimics our control flow. So that's too much code. Oh, we're one line off. Hold on. There we go. Beautiful. So remember we have a get iter instruction to start the loop. It goes here. It predicts for iter, which is great because it actually jumps down to here, and then in the for iter it does this. In the correct case where everything works, it predicts store fast, so it actually will jump to store fast if it works. So it just jumps to the next thing.
Oh yeah, store name, right?
Oh, store name. Yeah, that's right. So actually, it won't skip it. Good point. So it actually continues. So right. So this is actually an optimization. So it actually is store name. So what happens on this continue? Where are we going?
Like the gigantic loop.
The gigantic loop. We're just going back all the way top of that gigantic loop, and go back again. Right. Or just the next opcode. I mean, the next opcode was store names. Then we have to go back the gigantic loop. Okay. Good. So that means that when you have a for iterate, actually the buck kind of stops there, right? We're done with the for. Well, we're done right now. We're gonna go back to the top of the loop and do the next thing. But the only way the for iter ends is if we have an error, or we just get out. So all this code under here, only happens once at the end of the iterator. And if you notice how after everything is done, it says jump by op arg, and this is a jump. This actually jumps in our code. It actually moves the bytecode instruction pointer to jump. And then when we actually continue to go back to the top of the loop, we're actually in a whole other instruction. So where does the jump by happen? Jump by happens here. So in our code, the jump by is we're for iter here. It says jump by 11 really to 36. So jump by 11 spots to 36, which is right here. So when we're all done, when all said and done, we're going to jump to here, and then we're going to keep executing from there. That's okay. So, what is your question?
Yeah.
Jump by. Okay. So now we actually have. Now the thing to look into is iter next, right? What is this thing? So this is the most generic code because in CEval this says this has to handle any object with some iterator. So for the list, let's see what iter next is. So the list, recall, is a sequence iterator object. So if we're going to go object iterator.object.c, iter_object.c. Oh, actually, what are sequence iter objects? It's here. Right? This is a sequence iter object. So this is what we remember last time. So there's a pi object head because it's a pi object. There's an index, which is a number, and there's a pointer to the sequence. So remember in our thing, it points to some list, and the index starts out as 0. So that's all the sequence iter object is. It has two things inside. And you can imagine using this for lists or tuples or strings, anything that's a sequence. We have sequence iterator new. So now let's go to next. Iterator next. Okay, so here is the type sequence iterator. And what we're looking for TP iter next, right? This is the string we're looking for. So we just do a search. If you notice, if you have a text editor with a search function, it's very useful. So right here. And this TP iter next make sure it's in seek iterator. This is a seek iterator type for sequence. So remember this for your assignment because you're gonna have to go through these type objects. So iter next, that's the method we're gonna call. So we're gonna find this method, which is, is here. Now this method is called iter next, whatever, and then we're just gonna call it on the iterator itself. So what we're gonna do is we're gonna call, in our case, iter next with v as the argument. We're gonna call this thing, and that function is here, right? This iter, did I say iter next? Yeah. We're gonna call it here. Okay, so now we're gonna search again. All this is just simple string search. Iter next. This is the function. And see how I can barely fit on one screen. This function takes an iterator in as an argument. These are all pretty self-explanatory, the code. It first checks if it's a sequence iterator, just as a sanity check. It grabs the object out. It grabs the sequence. So if the sequence that it's referring to is actually null, then we just return null, we're done. Then, oh, look what actually happens. It says PySequence get item, IT index. Okay, so can someone describe what this, I guess the highlighted block does? So call it a list. A, B, C, and then IT sequence points to this. And now this says sequence is IT sequence, just as a shorthand, right? Sequence is that. So what is this? Well, first of all, what does this first line do?
Points to that guy.
Sorry?
It points the result to.
What is the result? What are we getting?
It just result is a pi object pointer, and then it just points to whoever is indexed by the IT index.
Okay, so right now the IT index is what? What was our IT index?
0.
It was 0. So it's basically this thing, right? It's whatever A is. So it actually uses the index, which we start at 0. I think we always start at 0. And then if the result is not null, what do we do with the index? Just increase it by 1. So the index now is 1 now, and then it's not 0, it's 1, and then 2, and so on. So this is actually the iterating thing, right? And we actually increment the index, and then we just return the result, and we're done. So we actually are relying on the fact that PySequence has a get item, and you can imagine digging in more. We won't go into detail. You can imagine digging in more. Whoa. Weird. You can imagine digging in this code and keep on going down a rabbit hole, and then you'll finally get to the list one. That is the list get item. And each data structure has its own get item. But the whole point of this iterator thing is this is where the rubber meets the road, right? This is the main iterator part where we're actually taking the index, getting the item out of it. We're actually using the index. This is like you're saying, was it X was our list? A, B, C. It's literally like you're saying X0, X1, X2. You actually are doing X0, X1, X2. It's just all hidden behind the iterator interface. But really, if you say, E equals X1, E equals X0, E equals X2, it's the same effective code that's executing. And the really important thing is you have to increment the index, because if you don't, then when you keep calling it, it's going to keep on giving the 0 thing. This is what it's iterating over. So if you can imagine iterating, the index plus plus is the iterating part, right? Every time you call it, it's going to iterate. And there'll be exceptions. If things go wrong, it will actually throw an exception. Actually, it'll set the sequence to null and return null. So it actually catches the exception if it's an index error or a stop iteration exception, which means if you try to go out of bounds on the list, it will give you an index error, right? So recall from the beginning of the hour that if you say x equals a, c, so we really just do an x0 and then x1 and x, syntax error, x3, it'll actually be an index error, which is list out of bounds. So if it does that, then we actually just set the sequence to null. It actually doesn't throw an exception in C. It just sets the sequence to null. And when you actually in the evaluator, does it return null? Let's see. I think it returns null. Yep, and it returns null. So null means something was done. We don't have anything to return. And if you actually look at here, if x is null now in the interpreter, it'll go down to our exception case and actually say we're done. So we actually signify that we're done by returning null as x. And this is like, I mean, this is a convention. Remember how we're in C code now. So C code, it's either, x is either a null pointer, right? X either is a null pointer or it points to some pi object. Right? And they use null as a special kind of indicator value for like there's something wrong or we have nothing to return. This is very confusing because Python has a none data type also, but none is actually a pi object. There's actually a pi object called none, which is the Python's version of null, but it's not the C version of null. And C null means 0, 0, 0, 0, like the pointer is null. So if you actually look at the bytecode, if you're looking at your bytecode, remember how always these things, these functions and modules end with load const none and then return. Doesn't mean that we're loading null. We're loading a special none object in Python. That just represents null in Python. Okay, so I think that's it for the list thing. So, so the next branch that we want to explore, which I don't want to go into too much detail because we'll actually have you do this assignment, is what happens when it's the other thing, right? So notice how getIter has two branches. It has the list one, and then it has the other one, which is the more general case of iterators that aren't a sequence. So the sequence iterator we did for list was just a special case because it's just an optimization for Python. Now let's actually look at defining your own iterators. So I'll mostly iter class use Python code here. So how should I post this code? This is on Stack Overflow, so you can, just a Stack Overflow entry. I just modify a little bit. Okay, so we haven't seen classes at all in Python, so I'll describe this very briefly. A class in Python is, imagine a class in Java or C++. There's a name for the class. The init function is the constructor, and all methods inside the class take a self argument as an explicit argument. Java calls it this. It's called self. What this class says is when I initialize it, I give it two numbers, low and high. And then, this is actually good. We'll just actually have you do this, use this exact example for the assignment. We initialize two numbers, low and high. And this sets self.current as the low one, self.high, which is, I guess, the last one to last one. And then when the iter method just returns itself, it happens that you can create a separate iter object, but this class is actually its own iterator. And think about that. It's kind of weird, but because this class has a next method, all iter will do is just call the next method. Right? All the iter will do is call the next method. So the iter here is kind of weird because you're returning yourself as your own iterator. But that's legal because all an iterator needs to do is just call next. We just need to be able to call next on it. And it just happens we define next. So what does next say? It says if the current number is greater than the high number, just raise the exception. Just say we're done. Otherwise, we increment the current and we return self-current. We have to return the old value. It's just a bookkeeping thing. So if we use this in a for loop now, notice how if we write a for loop. Actually, first of all, any questions on the class definition? Because I mean, for people who haven't seen the objects in Python before, I mean, we want to get this cleared up before. You'll need this in your assignment. And we haven't formally covered classes. But you can just look it up online. A lot of it is just syntax, but it's effectively just you have a method called a constructor, and then you have, these are just other methods you define. And it just so happens that this counter is its own iterator. So how do we actually use it? We use it in a for loop. We actually say for C in counter 510. That will create a counter. The for loop, like we saw before, will actually grab the iterator out of it and keep us calling next and assigning it to C. It so happens that this iterator is itself. Like the iterator is object itself. But you can imagine having a separate class that's an iterator over counters that points to counter. This just keeps it simple. Let's actually run this. Can actually not put this. So I class. I'm going to rename it. The reason why is we're going to Python. We're going to import I class. When I import it, actually runs. So iClass.counter is now a class. To create an instance of the class, we just make a counter. We're going to say 3 to 7. This is the actual instance of the counter. So x equals I class counter. So now if we want to say I equals x dot iter, so what should I be now? So, well, I isn't anything. It's an iterator, right? It's an iterator. So it's itself, right? It's weird because this x is an I class counter at this address. This I is also an I class counter at this address. It's the same thing because the iter just returns itself. And it's perfectly legal for it to return itself because as long as we can call next on yourself, we're good. So all it's doing now is now what we do is call I.next, and which should this return? 3, because this counter is 3, right? And then I.next again, 4, 5, 6, 7, and then it'll break. So nothing prevents us from making another. So if we actually make another iterator, what happens? What happens if I call I.next here? Ideas here? So it just return itself, right? Just return x itself. So I think this will still break, right? It didn't actually reset. So that's like has a disadvantage doing that. That doesn't reset. So imagine if you create if it's a whole new object, it could reset itself, but this doesn't reset itself. So it's actually not a great iterator, but it's the simplest one. So we need to actually create a new counter then. 3, 7. Oops. It's called I class that counter. So then we can iterate over it. So for element in C, print element, and that just again creates an iterator and does its thing. So the basic idea here is that again the next method not only returns something, it's very important it actually modifies itself because it needs to keep track of where it currently is, and so forth. So we'll go over this very briefly, but I don't want to spoil too many details because a lot of your assignment will be kind of figuring out the internals of how this works. So actually, you look at the bytecode. Bytecode's a little big, but if we look at the bytecode, this first part, so when we do the annotation thing for this, don't worry about this part of the bytecode. This is just, this creates the class. And we won't go over class until way later, I think, until basically 1 week from now. So don't worry about it, just, this creates some class. And then the key part here is that we have a setup loop just like we did before. We load the counter. We load 5, 10. We call, well, actually what this does, well, let me split up the code a little more. Sorry, this will actually look better. We'll just say C equals counter 5, 10. Make it a little smaller just make your assignment easier. Alt and C, print alt. I just split it into 2 separate lines. Should be the same code. Yep, 5, 6, 7. Okay, so all right. So now these 2 lines of code are kind of boilerplate, right? So don't worry about this line. This just creates a class. This line actually gets counter 5, 7, initializes it, calls the function, which is calls the constructor, and then stores it into C. So just C is some counter object. So we just know it's a counter object. And then here's the main body of the loop, right? That we have setup loop, and this sets it up, and when we're done, we're going to 56, which is all the way down here. And then load name, we're loading C in, doing a get iter, getting a for iter, we're storing it in elt, and then once we have elt, we're going to print it, and then we're going to jump absolute back to 41, which is up here. So notice how this for loop looks exactly like the other for loop for the list, right? The bytecode looks exactly the same, which makes sense because this bytecode, if you just stare at it, or if you stare at the source code, this for loop alone doesn't know what C is, right? In Python, everything's determined at runtime. It doesn't know what C is at all. It can only generate generic bytecode. It can't generate some special bytecode for like a counter object or something. So the kind of exercise, part of the exercise you'll have is figure out what actually happens now. And it's not the sequence iterator, if you imagine, because the sequence iterator was built into the list. Something will happen when you where is it? When cval.c. So for iter. Something will happen here, right? In this iter next, or also in this get iter. So we need to figure that out for the exercise. And the big hint here is that you need to look at abstract.c to see to see what this pi object get iter is all about. Okay, so I think we've covered all that we need for this class. We have a custom iterator. I need to fix a typo, and for loop over a list. Yep, and then iterators and for loops work.